Ta-da. Let's share this one. Take out your 2.6b homework. And with my myriad of tabs open. All right, there we go. Okay. Now, before we get to the actual homework, this was the choice on Monday for what they wanted my face to look like. And so like they looked at it and they're like, well, what about the left side of his face? I was like, well, it's probably just the same. But like, no, you have to shave. So we shaved this whole side. And I'm gonna like go even closer. I forgot to do that this morning. But then yeah, mustache like into like the weird like chin strap. Like I don't know, it's so weird. My favorite part though is like how long it is. Like you can see. Oh, it's so gross. It's never been this long. But there you go. This is how I look now. I know. Thank you. So thank you guys. I mean, $134 is huge. So you guys are a big part of that. You guys, just period 4 was $134. Total, $532 and counting. I actually have a student that said that if I kept this through like the rest of school until Thanksgiving, he'd give me another $100. So, of course, $100. That's huge. That's huge. That's huge. Looks awesome. All right, now I know wearing the mask makes it a whole lot easier. Everywhere, right? Grocery store too. Yeah. I'm down. I love the getting weird looks at the grocery store. Why not? All right, let's do it. Homework 2.6b. Hopefully, well, it's okay. I'm gonna wear this for now. It's starting to dig in though. I need another one. I do want to show off the amazing beard, at least a little bit. Hopefully 2.6b went okay. You're feeling pretty good about it because 2.7 starts today. So I want to make sure you're feeling good about like how to find this stuff comfortably. Basically looking at like a week from today, we will take our 2.4, 2.5, 2.6, 2.7 test. Okay. And by Friday's class, or by Friday really, I will have a plan for what's going to happen on what day, and what to expect both in person and then at home, right? Because you get those 2 sections. At least that's what I'm thinking. I just don't think 50 minutes in class will be enough. That's really what it comes down to. So there you go. Number 1 was already factored and simplified. Domain just can't be -5. X equals 5 is your vertical asymptote. No holes because nothing divided away. And the only thing new from Monday was figuring out the end behavior, right? And so for me, it's really a decision. Do I have a horizontal asymptote and where? Or do I have a slant asymptote? And because the degree on top is 0 and degree on bottom is 1, the degree on top less than the degree on bottom, always, always, always going towards 0. Because as x gets humongous, you've got 2 over 100, 2 over 1,000, 2 over a million, right, heading towards. Good? Sweet. Okay. 2 and 3 side by side just because I had the space. But I kind of divided them apart so you can see them. Number 2 needed some factoring, but nothing to simplify there. There were no common factors, top and bottom. So x over 2 over x, GCF, and then x minus 6. We want to get down to linear or unfactorable quadratic factors. That's kind of the hope, the goal. 0 from the first factor doesn't work. 6 from the second factor doesn't work. So that's my domain. So I'm going to start labeling it domain, not excluded values, but really that's all I'm going to write down are the values that don't work. And because nothing divided away, I don't have any holes. If I divided something away, that would have been a hole. But nothing divided because nothing to simplify, top and bottom. So both of those excluded values are going to be vertical asymptotes. And you see I wrote them separately, right? X equals 0 and x equals 6 written separately. 2 different lines that I want to keep track of. No holes, right? Because nothing divided away. And then for end behavior, part E, right? Degree on top is 1, degree on bottom is 2. Numerator degree is smaller, always y equals 0. Okay. Number 3 just got a little bit trickier. I just tried to throw some different kinds of factoring at us, right? Pulling out that GCF of 2 on top, but then hopefully you notice that you can still do more, right? You've got an x squared minus 4 left inside, so keep going. Right? We want to factor everything we can. So 2, x plus 2, x minus 2 on top, and the denominator, x plus 5, x minus 2. And then those two divide away, right? That x minus 2 right there, that x minus 2 right there. We can divide those away and just get a simpler version of that same function. But still recognizing that if I've got a degree 2 on bottom, I have these 2 linear factors, I should have 2 x-intercepts that don't work. 2 x values, sorry. Not x-intercepts. 2 x values that don't work, -5 and +2. But because I divided one of those away, that x equals 2 is going to create a hole, not an asymptote, right? The -5 is definitely an asymptote because it's still there. But the x minus 2 factors, so the 0 of x equals +2, is going to be the x part of the whole. How do I find the y value that goes with it? I plug it into the simplified version to see what happens. And 8/7 is not the answer we were hoping for, but that's okay. I'll just try to plot that as best I can. I'll go to 2, 1 and then just go a little above that, right? Because 8/7 is 1.1666666 like that. So do the best you can. And then that takes care of all the stuff that doesn't exist. We want to figure out end behavior though. So I go back to the original. I look back at my original function and I compare degrees. Degree 2 over degree 2. So with 1 and 2, I was smaller on top, so I know I'm going to 0. But now that we're the same top and bottom, it is the ratio of leading coefficients. 2 on top, 1 on bottom, 2 divided by 1, so y equals 2. Okay, so I'm going to have this horizontal asymptote that I'm going to graph at y equals 2 with arrows on the ends, and those will be my targets. That's what I'm going to head towards, either from the top or from the bottom on either side, and see what I get. And today we'll actually start graphing stuff, so that'll be good. Questions on 3? Okay, 4 I actually thought was one of the harder ones. Just the factoring part was the trickiest part. And I this stuff doesn't happen a lot with these difference of cubes, but it does happen. So I just want to try to keep that fresh, right? X cubed minus 2 cubed. So x, 2, x squared, 2x, and 2 squared. Same, opposite, always positive. Okay? But factoring the denominator is not visibly factorable, right? I don't see an algebraic kind of shortcut strategy on how to factor this cubic. It's like factoring by grouping is not going to work because I don't have the same relationship between these coefficients and these. So the easiest way to factor polynomials that are larger than degree 2 is to check for rational roots first. So here's what I did. I went to just plain old y equals in my calculator, and I didn't type in the whole function. I just typed in the denominator. So I had y equals x cubed minus 4x squared plus x plus 6, as if I was looking at just the polynomial of d of x. And I said, okay, I want to factor this. And if it's degree 3, I'm hoping for 3 factors. And I know I can find those, whether they're real or irrational or imaginary, it kind of depends on what we got. But I always check for rational ones first. But what numbers do I plug into the table to see what works? All of the possible rational roots, all of the factors of 6 over the factors of 1. Right? Rational roots theorem says look at all of the factors of your constant over all the factors leading coefficient. So all of the factors of 6 over 1. So 1 and -1, 2 and -2, 3 and -3, 6 and -6. And I just dropped those in the calculator. And what I got when I actually plugged those in is I got -1, 2, and 3 to all be 0. The table showed me 3 rational zeros, which means I can factor this using those zeros. Oh, -1 was a 0, okay, x plus 1. Oh, +2 was a 0, okay, x minus 2, right? And -3 was a 0, okay, x minus 3, and boom, 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 there are my 3, and I don't need to do anything else. It's cubic, I got 3 zeros, I'm done, I just write it factored. Okay, you see how I did that, right? Do that, super easy. So you're gonna have calculators for sure to do this stuff. Use them, for sure. Okay, the x minus 2's cancel. So I end up with this unfactorable quadratic at the top, and that will never be factorable, and that will never have real zeros. this leftover quadratic from sum or difference of cubes will never give you answers you have to go looking for because we're graphing in the real plane, so we're good. Okay. So there we go. My domain are the 3 x values that I found that don't work, -1, 2, and 3. But because I divided away the x minus 2 factor, I know that that's going to give me a hole. The other 2 will be vertical asymptotes. Write them separately. For me to figure out the -4, right, that y value that went with it, I just kind of came over on the side here and I plugged in 2 into the simplified version of this one. And magically, I cannot believe it worked out so nice. I got -4, which is really nice. There's a hole at that spot, and I'm good to go. Degree on top is 3, degree on bottom is 3, so ratio your leading coefficients for your horizontal asymptote, so y equals 1. I know it's a lot to remember, but you'll have all the skills by the end of today. 2.7, we're going to be done today, realistically, okay? Which means we're just going to practice, like, for homework Thursday, talk about stuff on Friday, and we'll have Monday to review for sure, okay? All right. Number 5, I just wanted to make sure that I threw a slant asymptote at you. So I factored the top, but nothing there to worry about because nothing divides away, but x plus 3, x minus 3, cool. So a linear denominator, so just one x value doesn't work, that -1. I didn't divide anything away, so it's not a hole, so it's an asymptote instead. X equals -1 is the equation of that vertical line that we'll dash. But I don't have a horizontal asymptote because my degree on top is larger than the degree on bottom. And to find that slant asymptote, we actually divide. Right? We are going to actually take x squared minus 9 and divide it by x plus 1. And you have 2 choices on how to do that. Because the denominator was linear. Because the denominator is linear, I can use synthetic division if I want to. But I wanted to show you long division so that we remember that. But don't forget, right? If you have a quadratic, I need a quadratic term, a linear term, and the constant. I need all 3 terms, so I had to drop in that 0x. I had to put that 0 in for synthetic division to make sure that I had a spot for everything. And it worked out real nice, x minus 1, cool. Y equals that quotient. X minus 1, there it is, right? Quadratic, do synthetic division, so it just drops down 1 degree. There's 1x minus 1. There's my slant asymptote. And when it comes time to graph these, we're going to graph those lines. Right? I'm going to have a dashed line with a y-intercept of -1 and a slope of 1. Right? Chapter 1 of pre-calc it started with some linear stuff, so we want to make sure we've got that. Cool? All right, let's actually graph these things. 2.7 begins now. Realistically, we probably can only do like 2 of these right now, but you're going to want to get some graph paper out to make the graphing easier. Does anybody need graph paper? Okay, I'm going to give you probably like 3 sheets of graph paper so that over the next couple days, you can use these. So graph relatively small here so we can utilize what we've got. And you're also going to need a straight edge. Some kind of straight edge. Doesn't have to be a ruler. It could be the edge of a credit card. Realistically, that's a straight edge. But if you want a ruler, I'm going to get them for you so that they stay clean. Who needs a straight edge? Need one? Yeah, I got one for you. Might as well use mine. That works. And take a calculator out as well. That's a bendy edge. You gonna use that? Sweet. Cool. All right. Let's do this thing. All right. What I want to give you today, I'm going to stop sharing. So folks at home, I don't know if I put this on Canvas. Let me do, let's see. Folks at home, give me 1 sec. Go to Canvas. Go to today's announcement. I got a link. This way you guys don't have to have my screen shared and you can watch us actually do the graphing. Give me a sec. I'm going to edit today's announcement. And there's going to be under Start 2.7, which is not linked right now. Now it is. Open up today's announcement, and if you already did, refresh it so that Start 2.7 is clickable. and that will open up a presentation that just has a few examples. Okay, but I don't want to share that screen. I'd rather.
Mr. Rosengren, saying you need to like request access to go on.
Let me change. Change link to DCSD. Try it again. Refresh. Re-click. Tell me if it works.
Yep,
all good.
Okay.
Yep. All right, so we're probably just going to do number 1 and 2 today. So if you guys have graph paper at home, that'll help. But I'm going to kind of bounce around a little bit between writing stuff down here and actually graphing on the projector. So like I'll turn it like this. So you might want to pin, if you haven't, you might want to pin me. I'll try to move it a little closer, but I'm going to do most of my work on this whiteboard in front to start. Okay, so here's what I wanted to give you all today. Was a pretty good strategy on how to actually sketch these graphs. And we're going to start with pretty simple ones, but the process doesn't change as we go, okay? But this is definitely something that, like, I could just go to y equals, type in this function, and know what my answer is going to look like when I'm done. And I, your teacher, I know that, okay? So I'm not worried about how perfect your sketch looks. What I'm more worried about is the work that you write down that if you didn't peek at your graph would have gotten you there, okay? So like this, what I write here is just as important, maybe even more so than eventually us getting to a good graph. Okay, but I'm going to look at both for sure. But what I want to start with whatever our function is, so let's do number 1. 3 over x minus 2 is exactly all the stuff we've started with already. So you're going to see that when I write all this stuff down, I'm going to do like the 2.6 part first. Okay, so we're going to start with, okay, like what's the domain? And don't worry, when it comes time to be tested on this, I'm not going to leave you to remember all the stuff to write down. I will say, write down the domain, the vertical asymptotes, any holes, like all that stuff. I'll tell you what you need to write down. And the easiest thing, of course, with domain is to just write down the excluded x values, whatever your zeros are from the denominator. So what number doesn't work? 2. Sweet. So that would have been part A, right? Write your domain. Oh no, part A would have been factor and simplify, but nothing to do there, right? 3 over x minus 2, nothing to do. Okay, so part B, find the domain. Write the excluded values, cool. Okay, part C, decide. For all of your excluded values, does that create a vertical asymptote or does that create a hole? And I want you to write down both. And if there aren't, like if it creates an asymptote but not a hole, say that, or vice versa. So which one is it? Is it an asymptote or does it create a hole? Why? Because plugging in 2 is only going to make the denominator 0, right? You would get 3 over 0, not 0 over 0. So how do we write that? How do I write the vertical asymptote if it's happening at 2? It's a vertical line, x equals, good. X equals 2, okay? It's a vertical line, so it's only ever going to cross the x-axis, so I just need x in that equation. So do we have any holes? Then write that down. None. Okay, make sure you are mentioning the fact that you have a hole or you don't, depending on what we got. Okay, cool. And then Monday's stuff was, all right, what's the end behavior? Right? Do we have a horizontal asymptote somewhere, or do we have a slant asymptote somewhere? What we saw on Monday is that if we want to figure out where our left and our right behavior are going to be headed towards, it's just a comparison of degrees. So I look at the function, I look at number 1, and what's the degree on top? 0. This is a constant, right? What's the degree on bottom? So degree on top is smaller than degree on bottom. Always, always, always y equals 0, which means we do not have a slant asymptote. I think that's a little extra. I think you can probably just say horizontal asymptote of y equals 0. You probably don't need this because it's one or the other. Absolutely. So I'm good if you leave that one off. Cool. And that's what we know so far. Welcome to the end of 2.6. Okay. Now the beginning of 2.7. Let's find some points that actually exist so we know what to plot. And if you were thinking about like plotting points on a graph that we definitely want to make sure we have, what do you think we should keep track of? Like, what are the most important points on a graph that we definitely want to have? What do you mean? Absolutely, right? We want to make sure that our asymptotes are there. But what about the points that do exist? Because that's now, like 2.7 says, okay, we figured out all the stuff that doesn't, and that's, now let's find the stuff that does. If you're looking at a graph, you don't have to, I'm just going to give you a visual, don't draw this yet, but if you had to put some points down on this graph, which points do you want to make sure you definitely have? X-intercepts and y-intercepts. Sound good, okay? Let's talk x-intercepts first. And what I'm going to do here is write the actual ones down for this function, but just in case you wanted to have some notes. Here's how we're going to find them in general every time. Okay, so we'll find x-intercepts and we'll find the y-intercept. It's a function, so we can have more than one x-intercepts or none at all. That's cool. But there's only ever at most one y-intercept because I don't want to have points stacked on top of each other because then I want to be a function. Okay. The x-intercepts happen when we go here in general when y is 0, right? I just want to make sure I have 2, 0 or 5, 0 or 1/2, 0, whatever it is. So how are we going to find the x values that make that work, right? You've got, I don't know, like you've got a fraction and I want it to equal, like I want to get 0 as an answer. Like I want to plug in an x value into a function and actually get 0 back when I'm done. Now, don't look specifically at this one, but just think in general. If you've got a fraction and you want to make the result of that fraction 0, what do you want to have on top and what do you want to have on bottom to make that 0? Was that the top, the bottom, both? So what happens if I put a 0 in the denominator? Can we actually divide by 0? So my denominator can't be 0. This just has to be some number on the bottom, and that number cannot be 0. I cannot divide by 0. In fact, remember, that's the number that we're keeping off of this whole graph, is making sure we don't plug a number like 2 in, because that would actually create 0 on the bottom, no good. But if we want to get an answer that is 0, and you've got some number on the bottom, 1, 2, 5, 12, whatever, what number has to be on top? Has to be 0. Okay? That's what I'm looking for. I want to find x values, whatever they are, some constant, right? Where this number is a 0 from the numerator only. Okay? X equals c is a 0 of n of x only. I want to look at my function and find values for x that are going to make the numerator 0. Because then I have 0 over whatever, and that's 0. And that's what I want. I want to run into the x-axis. Okay? And you could have 1, you could have 2, you could have 5, you could have none. Depends on what your function looks like. So look at this function. Do you have an x to plug into on top? No. So can it ever be 0? And that's okay. We might, that says none. none, we might not have any x-intercepts. Remember, horizontal asymptote is a line that we can cross. It's just a guide for the ends. So don't let the fact that y equals 0 is a horizontal asymptote and we don't cross it, that's just coincidence. We are allowed to cross it. But in this case, my numerator's degree is 0. That's how many x-intercepts I'm going to have if that's my degree. Right? If degree was 1, I'll find 1. If degree is 2, I can find at most 2. If degree is 3, I can find at most 3. 4. Cool. Nice. All right, so that's x-intercepts. In this case, we don't have any. Our y-intercept is going to be the 1 point, 0, comma, something. All right, where x is 0, and we go up to some number. So I'm just going to put a c again there. Right? It's some constant, some nice number. But we want to try to find this as easily as we can. I don't want to have to do much investigating. I want to see if I can find this pretty quickly. So think about it, right? Plug in 0. That's really all we have to do. What happens to this function specifically, to actually g of x, if we change every x to 0? Negative 3 over 2, right? Negative 3 halves. Perfect. And really what it comes down to, okay, so y-intercept 0, comma something, and in this case, negative 3 halves, negative 1.5. What you're going to see is that no matter what the function is, if every x becomes 0, the only thing that you'll ever have left are the constants at the end. Right? Whether it's, 0 over negative 2 or negative 9 over negative 3 or negative 2 over negative 1, whatever it is, this number right there, that y value for every, and it's the only one, that c will always be your ratio of your leading, your constants. The constant on top over the constant on the bottom. 3 over negative 2, done. Negative 3 halves. Love it. Looks good. Okay. And when we think about trying to graph this, how many points do we actually have written down right now? We only have 1. That is not nearly enough. We're going to want to find a bunch more. Okay. How many more is up to you. But think about what you've got in terms of x's that are guaranteed. I only have 2 of them, right? I've got 0 and 2. I got an asymptote here and I've got a point here. And if you want to graph this thing well, I'm going to come over here so people at home can see it. If you've got these 2 points, whether it's points or asymptotes or whatever, you got 2 x values. Bare minimum, I'm going to go like this, okay? Bare minimum, you need something before that first point or asymptote, something in between, and something after. So if I have 2 x values, I need at least 3 more points. I'm realistically probably going to find more than that because I want to get a sense for how this graph flows. Now, the nice part about rationals is that just like polynomials, they're smooth, they're rounded, they're gentle, right? But they're not going to happen quite the same way because we're going to be heading towards asymptotes, and we want to figure out, like, am I going up towards the vertical asymptote, or am I going to go down? Right? Am I going to come down from this side, or am I going to come up from this side? Because as I get closer to an asymptote, remember, I want to approach infinity or negative infinity as I get closer and closer to it. That's what a vertical asymptote is. And if you give yourself a nice collection of points, like I need right now a bare minimum of 3, I'm probably going to find like 4 or 5. I'm probably going to do like 2 on this side, 1 in between, and then 2 on that side. But what you want to try to give yourself from here is a collection of points that will help you fill out your graph. how many is up to you, but you need at least one more than the number of x values you've written down. And I've circled them right now. All of my x equals, okay, x equals 2 and x equals 0 have given me spots. And what I'm going to show you today is not necessarily how you have to write it down now, but I will tell you what, when we get to calculus, this is how we're going to do it when we start looking at a lot more specifics when it comes to it, okay? So here's what I'm going to do. I got these two x values, okay? Take a look right here, just at me for a second so you see why I'm going to do what I'm going to do, okay? If I've got two x values, it has that's a word. It is broken this function into three sections, right? One before it, one in between, and one after, okay? What I've got is an interval, a stopping point, an interval, a stopping point, and an interval. And when I design this collection of points, I'm going to start doing this in two rows. Now, you don't have to do it this way, but I'm telling you, you get to calculus, you're going to want to do it this way, where it's going to go interval, stop, interval, stop, interval, okay? So I've got this interval before I get to my very first x value, and I'm just going to go left to right. So when I look at the x values that are circled right now, you don't have to circle them, but that's what you're looking for. What's the first one left to right? Like negative infinity to infinity. What's the first one? So interval, where should I stop? X equals 0. And we'll figure out what that interval is, okay? Interval, stop. Interval, what's the next place I should stop? What's the next x value that I have circled in my list so far? Well, there's 0. What's the only other one? 2. Interval, we're going to stop at 0. Interval, we're going to stop at 2. And if I had like 3 x values that I cared about, okay, interval, stop, interval, stop, interval, stop, interval. If I had 4 x values, interval, stop, interval, stop, interval, stop, interval, stop, interval. Because I just want to fill in those empty gaps in between the stuff that I know exists, whether they're asymptotes or holes or x-intercepts or y-intercepts, whatever they are from this top list. I want to make sure that I stop at these points along the way. I'm telling you, when you get to calculus, it's going to be huge, okay? So if I'm starting way over here on the left at negative infinity, that's where that interval kind of begins. Hi, Miss Eaton. How you doing? Good. Nice. That's a big old stack of paper. Nice. Good. Okay, so we're going to go from negative infinity all the way to 0, whatever that number is, and just stop right before we get there. And then we'll go from 0 to 2 and stop. And we're going to find some points in these intervals. So, like up here, this row are intervals and stopping points, I guess I could call it. Okay, my collection of points, or like what's happening, is going to go in the row right below it. Like you're going to see, we're going to like look at characteristics and what's happening along the way. Okay, and then 2, and let's just go forever to infinity. And I know what's happening at 0, right? I have a y-intercept at 0, negative 3/2. And I know what's happening at x equals 2. That's a vertical asymptote. What I want to do in the intervals in between are find some x values that I like. Pick 1 or 2 points, or 3, or 4, or 5, or as many as you want. The bigger the interval, the more points you're probably going to want in it. Okay, this interval is huge. 1 point might not be enough. Right, this interval is huge. 1 point might not be enough. This interval is pretty tiny. Maybe 1 point would do it. Okay, but that's up to you. Maybe you find 2. That's okay. So what we're going to do is we're going to look at this function. I'm going to share my screen for a second for the folks at home, because I'm just going to take out my calculator. I'm going to plug in my function, 3 over parentheses x minus 2. And I'm going to go to my table, and I'm going to pick as many points as I want in that interval and plug them in. Okay? Realistically, in an interval this big, I probably want at least 2 points. Okay? Maybe 3. Maybe even 3. Or 4, or 5, or as many as you want. That's up to you. Okay? That's up to you. So, pick a point between negative infinity and 0. All the way over here to 0. Usually what I do is I start from negative infinity to 0. What I start doing is I kind of go to this number endpoint, and I start working my way backwards this way. So 0, no, I can't include that. I know what's happening at 0. Let's pick a point just to the left of 0. Let's see what happens at negative 1. We'll plug it in. And then maybe another one, like how about like negative 2? And negative 3, and negative 4, and negative 5, as many as you want in this space. And all I'm going to do is I'm going to go to my calculator and plug them in. Let the calculator do all the work. We'll do it all in one shot here in a second. Okay? I know what's happening. X equals 0. Done. Moving on. The interval between 0 and 2. Yeah. I love, given the choice, to go halfway. If I'm between 0 and 2, remember, these are intervals. Okay? These are points. So I know the table's a little confusing. You just want to think about what you're doing. I'll plug in 1, because that's halfway between 0 and 2. Or 1/2, or 1.5, or pi over 7, whatever you want, but pick nice numbers. It makes it a lot easier. Okay? I know what's happening at x equals 2, so I know what to do there. Let's pick, I don't know, at least 2 points bigger than 2. Let's stay close to this number. 3 and 4 sounds great. Let's see what happens. Okay? Now, you might plot those and say, you know what, I still don't know exactly what I want this graph to look like, how to connect those yet. Fine, get some more points. That's okay. I go to this, and I plug in negative 1, negative 2, 1, 3, and 4. And I just write them down. So at negative 1, I've got a point at negative 1. At negative 2, I'm at negative 0.75. At 1, I'm at negative 3. At 3, I'm at 3. And 4, I'm at 1.5. And maybe you plug in 5, and 6, and 7, and 8, and as much as you want. That's fine. Okay? I know I'm going through this rather slowly, and it's okay that we do this slowly. I wanted to get the first one really done well for you as best I can. Now we can graph. Okay, so now I kind of stop, and I start looking at my piece of graph paper, and I want to design a space that works. Okay, I got to make sure that whatever points I've got, I can fit them, and then a little bit more. All right, I'll go a little bit left, a little bit right, a little bit up, and a little bit down. And so take out a piece of graph paper. I'm going to take out mine. Graph paper. And let's design a space that works. Okay, you have a straight edge. Anytime you draw a straight line, you have to use it, even though we're sketching. Okay, we got to make sure we take out that straight tool and we get ourselves a space to work. So I'm going to graph my axes. There's a y-axis. There's an x. It doesn't have to be relatively big. You can make it about like a quarter of the size of the page. I'd say between a quarter and a half is big enough. Okay, and we know what we need. We need arrows. We need labels. X-axis is x, your y-axis is the name of your function, so this one was g of x. And we need a scale. And I'm just going to pick a scale that works. I've got whole numbers, and I've got some fractions and stuff, so you could go by ones. You could go by halves. You could go by quarters. You can make it as big as you want. But plotting things like 1.5 can happen if your scale is 1, right? Just go halfway in between, right? Plotting things like negative 0.75, that can happen. You just try to do your best. So what I'm going to do, because I know I have to get all the way to like 3 and negative 3 and 4 and stuff, I'm going to make, for me, like all of my pole boxes. So for you, maybe just like a box. It's just worth 1. Because that'll get me to, like, my biggest X value that I want to get to is 4. And I have a box bigger than that. Negative 1, negative 2, negative 3, negative 4, negative 5 is where those would go. And remember, you don't have to write down every number. You just have to plot what one box is worth, and then you're good. Again, I look up and down, and I look at the kind of Y values that I have to make sure I fit. My lowest Y value is negative 3. So I want to get down to at least negative 4, negative 5, right? My biggest Y value from this collection of points, right, is 3. So I just want to make sure I get up to like 4 or 5. So I think if I make going up by ones, right, that gets me to 4 up there, negative 1, negative 2, negative 3, negative 4. I can get to negative 5. That's pretty good. If you don't like the way it works, change it, fix it. I'm going to turn off the light so it takes the glare off. The glare is still there. Ooh, booby trap. That was close. Let's do this. Yeah, I'm done. It didn't really make a difference. All right, cool. I'm gonna turn the lights back on. All right, let's plot what we've got. I always start with what we started with, asymptotes. Okay. I don't have a straight edge, so mine's gonna look a little sloppier than yours. But you're gonna use a straight edge. I'm gonna graph a vertical asymptote at x equals 2. Okay, if I had a straight edge, this would look a lot nicer. Okay, it is a vertical line that is dashed, dotted. And you could just like graph the whole line and then erase sections of it, that's fine. Okay, arrows in the end, so they go on forever. And I'm just going through my list, kind of the order that I did it in. Okay, so vertical asymptote, done. No holes I have to worry about. Okay, end behavior. I have a horizontal asymptote on a line that's already drawn. So here's how I do that. I like color, so I'm going to use a different color to make it stand out. But what you could do is you could just go like a little below or a little above. But something else that I'll do to really make it stand out, when I graph it, I'm going to go past the arrow on the right, past the arrow on the left, and I'm going to label it. I'm going to put a little HA for horizontal asymptote, so whoever's looking at this knows what that red dotted line means. Okay, use a straight edge, it'll look nice. But you can go a little below, a little above, you can use color, you can make it just thicker, whatever you want to do to make it stand out. But I like to put my arrows kind of going past the arrows on my axes. Okay, cool. Nice, okay, so first column done. Okay, start collecting some points. All right, so I've got a y-intercept at 0, negative 1.5. So there's negative 1, there's negative 2, halfway in between negative 1 and negative 2, put a point. And if we had not gotten a collection of points down here, that's all we would have had to go by. And that is obviously not enough, which is why this collection of points down here is going to be so important for us. So let's just plot those two. Negative 1, negative 1. Negative 2, negative 0.75. Halfway between negative 1/2 and negative 1. And maybe you like got like 3 or 4 more points. Like maybe you saw what happened at like negative 3 and negative 4 and negative 5 and negative 6. And what you would see happen is exactly that. That as we start moving towards the edge, the left edge of the graph, you're going to get closer and closer and closer to that asymptote. That's the idea. It's a guide, it's a target. And what you'll notice is that as we're getting closer to that asymptote, what we want to be sure we mark down is that this graph is going to keep going. So I'm going to draw an arrow right next to the arrow for my asymptote. You can see I'm drawing this thicker so you can tell the difference between the graph and the actual asymptote. Or you know, maybe you just use a totally different color, right? Maybe you say, all right, I'm going to draw my axes in pencil, I'm going to draw my asymptotes in pencil, but maybe I break out something of a different color to really make this thing stand out. And what you want to start recognizing is that those arrows for your asymptotes are your targets. And you're going to have arrows either below or above your horizontal asymptote, to the left or to the right of your vertical ones. Okay? And when we're talking about horizontal asymptotes, it cannot be points above and below. That's why it's an asymptote. We want to approach it, but not usually cross it. Okay? Nice. So there are some points to the left of 0. We have our 0. We also have the point 1, -3. And maybe you want more. Maybe you're like, you know what? Maybe I want to see what happens at like 1.5 and 1.75 and 1.9. And what you'll see is you're going to start, so however many you want, you're going to start getting closer and closer and closer to that asymptote. That you're going to have this arrow right next to an arrow. You will always have those side by side to give you a guide. Okay? And we've got a point at 3, 3, 4, 1.5. Maybe you're like, that's not enough for me. Maybe you say, I want to see what's happening at like 2.5. And, you know, like 5 and 6 and whatever. And what you're going to see is you're just going to get closer to this arrow and closer to that. And so next to every arrow that you drew for your asymptotes, you will have an arrow for your function. And then we connect arrow to arrow. Left arrow to right arrow. Left arrow to right arrow. And you compare that graph to the one that you probably looked at before you even started this function, the one in your calculator. And you see how close you got. Right? And if your scale is off because you created a different scale, then you can always change your window to make sure that they match. Okay? Now that was the super long, drawn out version of how to get these done. And so what I'd like for us to do on Friday, I'm going to give you a couple to try before Thursday as homework. Call it 2.7a. But Friday, if you can come, I won't mandate it, but I think you should. Okay? I will see you live Friday if you can. And it's just going to be a practice. I just want to practice with more of these so you get the hang of it. Okay? Join if you'd like. If you have someone else going on, if you can't, that's fine. But I highly recommend, but I will not mandate your attendance on Friday. Questions? Yes. These, or how I chose the intervals. Okay, so when I start thinking about where I want to look for some points along the way, what I do is I haven't done any of this yet, right? But I have done 2.6 and the beginning of 2.7 with just my intercepts. And what I do is I look at my asymptotes, my holes, and any intercepts, and I make a list of them from left to right. And so I look at this list, and I circled the ones that have x values. X equals 2, over here, and x equals 0. Okay. So there's a black bin in the back, because those are dirty. I'll clean those. So I've got these two x values, 0 and 2. And those are going to break the graph into 3, you're welcome, 3 sections. Before the first one, in between, and after. And I just want to write down those intervals. So I've got these 2 stopping points with these 3 intervals. So I know that I've got some interval over here. But I better make sure I stop at 0. And I've got some interval here, but I better make sure I stop at 2. And I've got some interval after. All right, so here are my 2 stopping points. I want to figure out the 3 intervals that breaks it into. These are going to go on forever, so I better start as far left as possible. And then I stop at this number. And then I go from this number to this number, from 0 to 2. And then I go from 2 to the next one, and then from the next one to the next one, and the next one to the next one. Or once I run out of stopping points, then I just go on forever. And so it'll always go from negative infinity to infinity. But I just want to stop at all of the known x values that I know are important. Asymptotes, holes, and intercepts. And by creating those intervals, it just gives me a place to start looking for other points, just to give me, like, I don't know, like, you ever do those, like, connect the dot, like just coloring book, kind of like make a picture? The more dots you have, the easier it is to tell what the picture is going to be before I actually connect them, right? If I only have 1 or 2 points, I don't know what the picture is. But if I've got 10, 15, or hey, 1, 2, 3, 4, 5, 6 points, it gives me a better idea of how to connect them to make the picture that I know I'm going to end up with. Right? I know it looks like a kitty cat, but if you only give me 3 points, I don't know it's a kitty cat. You know what I mean? So creating a list, a collection of points in those intervals makes drawing that picture so much easier. And man, having that table where I can ask for whatever x values I want makes it really easy. And so like I just kind of like look at the only number in this interval and I just go close. But I got to be left of 0. All right, so -1, -2, -3, -4, something like that. Absolutely. So it could go negative infinity to -2, and then, but then I would definitely stop at x equals -2. Like this would have been an asymptote, a hole, or an x-intercept. And then I could go from like -2 to -1 because maybe -1 was another point I wanted to stop at. And then from -1 to 3, and 3 to 7, and 7 to 12, like whatever we've got, I'm going to try to keep the points relatively, like the x value is pretty close to 0, so that our graphs aren't this long. But as we get further up, we're going to have like 2 or 3 vertical asymptotes and a hole over there. And so we're going to have a lot of different sections. But having interval, stop, interval, stop, interval, stop, interval, stop, interval, stop kind of laid out from left to right, it's going to make graphing this a little bit easier. And when we start getting to calculus and we start trying to find relative extrema and is the graph going up from left to right? Like we won't need as many points when we have the calculus to go with it, because I'll be able to tell the type of curvature. I can be able to tell whether it's increasing or decreasing in that interval, and I won't need quite as many points. But we're going to do interval stop, interval stop, interval stop, interval stop as we do that.
That was really yeah. How you got I was like 0, and I was like, wait, what?
Yeah, it's really just me going back to saying, okay, where are my asymptotes, my holes, and where are my intercepts? I'll always start with those, and whatever x values come from there, those will all be my stopping points along the way. Okay. So come Friday, because I'll do like 2 or 3 more examples. We're gonna need those, and then we have Monday too to review for sure. Thanks, girls. See ya. Any questions at home? Anybody? Sweet. All right. Thank you for being here, and I will hopefully see you Friday.